All right, in this video, I'm going to explain something about complex eigenvalues that is just like it's typically pretty confusing. But if you look at it the right way, this example will show you why you do what you do with complex eigenvalues. I guess the part that's confusing is like, wait, why do I do it? Because there are some shortcuts that we always take, and this is the reason why. So I'm going to use this system to demonstrate what we're doing. You do need to know Euler's formula, which is e to the it is cosine t plus I sine t. If I were to put an a in here, I would get an a here, and an a here, and an a there, and there, and there. The negative here is because of even and odd functions, and I'm not going to go over that in this video. So let's solve this system. Um, with this system, I get lambda squared. My trace is 0, so plus 0 lambda. And then my det is 0 minus that product. So that gives me plus 1 equals 0. That's lambda squared plus 1 equals 0, which gives me lambda equals plus or minus I. So from there, I'm going to work this out in the complete way and then show you where that shortcut is. So I'll take lambda equal to I, and then here I'll do lambda equal to negative I. Now, when I do the I need to subtract this along the diagonal. So when I do that, I get minus I minus 1, and then 1 here, and then this guy gives me another minus I because I'm subtracting it along the diagonal. Now, you could like try to wrap your brain around this, or you could just use some of the tricks that we've learned before. Remember, we can flip a row and negate one of them. So I'm going to take the easiest one to do here, which is that right there. I'm going to flip them, so the I will come first, and then the 1, and then I'm going to negate the I piece, because then they'll both be positive. So I get I and 1. Next, I'll do the other one. So I'm going to, that was an I, so I subtracted it. Now I'm going to do lambda equal negative I. When I subtract it, I get a double negative. So I get, sorry, not negative, come on. I get a positive I, negative 1, and then 1, and positive, whoops, I'm just going to write I. So I would take that one if I could, but it's going to mess up the math that I'm trying to demonstrate to you. So typically, I think you would say, "Oh yeah, let me take 1 I," just like I kind of explained over here. But instead, I'm going to take this row. So that is going to look like I negative 1. So let's go ahead and do this the way we would do it if we had real eigenvalues. X would be C1 times I1 e to the it plus C2 times I negative 1 e to the negative it. So before I go any further, I guess I should say that the whole process here, like most of the work that I'm doing here is going to get shortcutted out, and I'll cross it all out at the end. But I want to demonstrate the long way so you can appreciate the short way and see why the short way works. So what I'm going to do now is expand that, and I will expand this. So I'm going to expand those two pieces separately. So let's do the first piece. Let's just look at this right here. That guy is I times 1 times e to the it, which is, 1, I1, all right, e to the it, rip it from Euler's formula, I get cosine t plus I sine t. And then I can FOIL that out, or I can distribute that stuff out. So that gives me the I gets multiplied by the top row. I gets multiplied by these guys, and then gets put in the top row here. That gives me I cosine t. And then I get a I get a negative because I square I. I get I times I. It's I squared minus, because remember, I is root -1, so when I square it, I get -1. So I get minus sine t. And then in the bottom row, I just get 1 times that. So I'm just going to write that as cosine t plus I sine t. And then because I know where this is going, I'm going to split these into the real and imaginary pieces, which is I times, cosine t. And then in the bottom, I get a sine t. That is this and this piece, plus the real stuff is my minus sine t and my cosine t. So usually, like if I want you to think about the shortcut. 1, we wouldn't have done this, and we wouldn't have written any of this. We would have done this, and this would have been our work. And then at this point, you are essentially done the problem. So just keep in mind how much more work I'm going to have to do to show you that that's the trick that we're going to use. But just as we look ahead, that is the work that we do to figure out the solution to this differential equation. So let's keep rocking here. All right, let's do some purple. This, I'm going to expand this one out in the same way. So that gives me I -1 times, all right, now this, I'm going to use Euler's formula, and I'm going to expand it out like that. So I get cosine t minus I sine t, which, let me do the same work, gives me, all right, I cosine t, and then I get I squared, but it's got a negative, so actually plus with a double negative, sine t. And then this gives me the negative version of that row, which is minus cosine t. And then I get a double negative plus I sine t. All right, so let's sort it. We get this is equal to I, boom, boom, plus boom, boom. And now I'm going to fill it in. All right, in the top row, I get a cosine t. In the bottom row, I get a sine t. Notice those guys match each other. They're the same thing. So I'm sort of just getting that out. And then I get a plus sine t is a real component here, and a minus cosine t, which is the real component there. Notice that is the negative version of this thing. So now what I'm going to do is rewrite this. My x of t solution equals C1 times, and I can just copy this. Put it right there. And then plus C2 times this stuff, right? So let's copy that. Boom. So now, let's keep rolling with this. What I'm going to do is distribute all of this stuff out. So this gives me C1 times I times cosine t sine t plus C1 times negative sine t cosine t plus C2 I times cosine t sine t plus C2 times sine t negative cosine t. So what I want you to see now is that this term is, it matches with this term, sort of. I guess I should have done the other one first. So let's look at this term right here. It matches this term right here. So I could write that as, cosine t sine t, right? That is this piece and this piece, but then it's got C1i plus C2i. So I'm going to write C1 plus 2i. That accounts for all of this and all of this. So I could do the same thing with red, but I just have to have a little negative in there. So I get plus, open parentheses, I'm going to take a positive C1, and then notice if I negate this, I get that, right? So I'm going to say C1 minus C2 times sine t, negative sine t, because I'm taking this one, cosine t. So from here, this is my x of t. So I can write x equals. And what I want to do next is say let C1 plus C2 equal a new constant, C3. And I'm missing a piece there, my I. It's very important. So basically, I am letting this entire thing equal a C3. And what that's going to do is give me x equals C3 times cosine t sine t. And then I'm going to let C1 minus C2 equal a new C4. And what's that give me? Plus, well, if this is a C4, C4 times negative sine t and cosine t. So, and then that is like, that's my solution. That is my answer. Because look, do you see that there's no imaginary pieces in here, right? So you may not be convinced that I can do what I just did, that I can convert this to this. Because you may say, hey, come on. This is C1 plus C2 times an imaginary number. You can't just say that that is C3, which this is imaginary, and then this is not, right? And then here, these are real, right? So so if I take C1 and C2 to be real, and I add them, boom. But if I take them to be real here, then I got an I. But I actually have a trick for that. And I'll show you how we do that right here. So look, if this is just one example. If C1 is equal to 5i plus 2 and C2 is equal to 5i minus 2. Well, look, if I take C1 plus C2, if I add these two things, I get these guys cancel. The 2's cancel. And I get 10i. So what I would get is C1 plus C2 times I. That gives me 10i times I, which squares out the I and gives me real. So negative 10. And then watch what happens if I subtract these. If I do C1 minus C2, that gives me, all right, when I subtract them, the 5's cancel with each other, and I'm just left with reals. So I get, what do I get? 2 minus a negative 2, which is 4. And see, that makes C3 and C4 both real. That tends to be the spot that people get hung up on the most here. Wait, you can't do that. And I say, yes, I can. I just have to very strategically choose my C1 and C2 to be complex numbers, and then it will work. So let's talk about the shortcut. So look at all this work here. The highlighted and yellow stuff is the only stuff you have to do when doing these problems. You don't have to work out both parts of the solutions. Here's why. Look at this. Cosine and sine, cosine and sine. And then look over here, negative sine and cosine, negative sine and cosine. You can just do one of your eigenvalues, plug it through, get the real part and the imaginary part, and those two become your solution sets. Because notice, they're the same thing, right? You don't have to do all the work twice. This will work 100% of the time when we have complex or imaginary eigenvalues. So we don't go through this whole step. We only do the highlighted. And I hope you can, two things. One, you see why, and two, you appreciate that doing the yellow highlighted work is much easier and better than doing everything else.